So in this video, we're going to start solving questions from exercise 13.1 and which belongs to chapter number 13, surface areas and volumes. So in all total, we're going to see 5 different problems. Okay. First, let's start with problem number 1. Now, the question reads, a plastic box 1.5 meter long, 1.25 meter wide and 65 centimeter deep is to be made. Okay, so we have to make a plastic box with these dimensions. Okay, let's use a highlighter to highlight these dimensions. So it has to be this much long, this much wide and this much deep. Now it is opened at the top. This is a very key information. The plastic box is to be opened at the top. Okay, ignoring the thickness of the plastic sheet, determine. So there are two things to be determined. First thing, the area of the sheet required for making the box, and second thing, the cost of the sheet for it if the sheet measuring 1 meter square cost rupees 20. Okay, so from this problem description, it's very much obvious that the plastic box that we are going to make is a cuboid in shape. Okay, so that's the first thing that we must note down, that this plastic box is a cuboid. Okay, the shape of the plastic box is going to be a cuboid. Now, so cuboid, is rectangular in shape. The base is rectangular in shape, and it will have 3 dimensions. Every cuboid has 3 dimensions. What are those 3 dimensions? In fact, let me note it down. The 3 dimensions are length, okay, and breadth, okay, and height. So these are the 3 dimensions that a cuboid has. Now let us try to draw this plastic box, the cuboid, with these dimensions. So let me draw this as the base of it. So we all know that a cuboid has a base which is rectangular in shape. Okay, and then it will have a height. So let's try to draw height. Okay, yes. So obviously this is not very much to the scale, but still just for us to help to understand the problem, we can draw it. Yes. So this is roughly how the cuboid, the plastic box, is going to look. Now let us try to assign these dimensions to the box. So it's 1.5 meter long. So I'm just going to say, so length is equal to 1.5 meter. Okay, so let this be the length. And let this be the breadth. So breadth is going to be, okay, so breadth is going to be 1.25 meter. Okay, and then we have 65 centimeter deep. Let that be the height. So this is going to be the height. So this, let the height be equal to 65 centimeter. So I'm going to write 0.65 meter. Now this is very important. This is in meter, this is in meter. So this dimension should also be in meter for our calculations of the surface area of the cuboid. So let this height be equal to 0.65 meter. 65 centimeter is 0.65 meter. So these 3 dimensions, length, breadth and height for the plastic box are now assigned. Now one key information is, which we have highlighted, is it is opened at the top. So this top of the cuboid is open. Okay, it's not a closed, which in fact means that the number of faces, that the cuboid will have is equal to 5. So let me come a bit to this side. Yes, so okay, let's draw a demarcation line here. So number of faces for the plastic box, okay, for the plastic box is equal to 5. This is very important. The number of faces that the plastic box will have is 5, which means the formula that we have to calculate the surface area of the cuboid cannot be directly applied in this problem, because that formula assumes that there are total 6 faces for the cuboid. Okay, which is what is a general or normal case. But in certain problems, if it is mentioned that it is open at the top, then you have to be very careful and understand that there are only 5 faces that the cuboid will have. Now let us try to calculate the surface area of this. So let's come it down here. Okay, so let's go rectangle by rectangle. Let's try to trace it down. So this is one rectangle. okay, which has these dimensions, length and the breadth. Now the top rectangle I'm not going to highlight because it does not exist. Okay, uh, the top of the plastic box is open. So okay, let's start like this. Point number one. So face one has the area. So let's write the area. Area of face one is equal to length into breadth. Okay, that is equal to 1.5 into 1.25. Okay, now let's come to the second point. Now before that, let's get rid of this highlighted face. Okay, so yes. Now the second rectangle is this one, okay, and this one. Okay, both are equal to each other. And what are the dimensions of this rectangle? The height is 0.65 meter and this is 1.5 meter, and there are two of them. Okay, so I'm just going to say area of face 2 and phase 3, let's call them phase 2 and phase 3, is equal to, so we are going to say 2 times, this is 2 times the length into height. Okay, L into H, this L and this H, this H. So that is equal to okay, what we can do is let's not substitute the values of L and H right now. We can use them later on when we do the addition. Now let's get rid of this highlighted thing. Now the third one is this rectangle, this rectangle, and this rectangle. They are also 2 in number. Okay, so I'm just going to write here point number 3. Area of face 4 and face 5, okay, is equal to 2 times, okay, because there are two of them. Now this is breadth B and this is height H, so it's B and H. Same here, B and H. Okay, so it's going to be B into H. Yes. So thus, for this plastic box with the open top, that's very important information. With the open top, we have the areas of all the 5 faces. L into B, which is just one face, which is our base. Then we have this 2 L into H, and we have 2 B into H. So that's it. So that's all. The area of the sheet required for making the box, which is equal to the total surface area of this plastic box, is going to be the addition of these 5 faces. Okay, so first let's clear this, the highlighted thing. Okay, let's come down, and thus I'm going to write here, thus total surface area of plastic box, okay, is equal to, okay, yes, that is equal to length into breadth. I'm going to use a highlighter, which is this one, plus it's going to be 2 times L into H, okay, which is again going to be this one, and this L into B is L into B, okay, and that is also, and then plus 2 times B into H, okay. What is B into H? This one, 2 times B into H, 2 times B into H. So all the 3 areas of the faces are here. Now all we have to do is substitute the values of L and B and H into this equation. So let's do it. So before that, let's see if we can do some optimization. So let L into B remain as it is, and I can take 2 as common. Okay, so that is going to be L into H plus B into H. So something like this, L into H plus, okay, B into H. Okay, just taking that 2 common. Now let us substitute the values of L, B and H. So L, okay, L is 1.5 meter, so I'm just going to write it here. 1.5 meter into B is 1.25 meter, that is 1.25 meter, plus 2 times L is 1.5, okay, and I think h is 0.65. Yes, h is 0.65. So let's come down. H is 0.65 plus b is 1.25 into h is again 0.65. Okay, so this is our area. Now we have to just solve it. So that is going to be equal to, okay, so we have to do this decimal multiplication. So 15 5s are 75, 7 gone carry. 15 2s are 30 and 37, 3 gone carry. 15 1s are 15 and 3, 18, and 2 and 3 decimals. So this is going to be 1.875 plus 2 into, what I'm going to do is 0.65 and 0.65 are common. So I'm going to take it out. So 0.65 is inside, sorry, outside, and 1.5 plus 1.25. Okay, that is equal to 1.875 plus, what is 2 into 0.65? That is equal to 1.3. Okay, into, what is this addition? It is 2.75. Okay, 5, yes, 2.75, that's correct. Now this will be equal to 1.875 plus, we are going to do this multiplication, 1.3 into 2.75. Now, how do we do this multiplication? You have to use the table of 13. 1.875 as it is plus 13 5s are 65, 5, 6 gone carry. 13 7s are 91 plus 6, that is 97. So 7, 9 gone carry. And 13 2s are 26 and 9 is 35. So this is 35. And we have 2 and 1, 3 decimals here. So 1, sorry. So 1, 2, 3. So 3 decimals will go to your decimal point here. Okay, now we have to add these two numbers. So 5 and 5, okay, so 5 and 5 10, 0, 1 1 carry. Should I use the highlighter? Okay, so 5 and 5 10, 0, so 1 1 carry. And then we have 7 and 7, that's 14, and 1 1 carry, 15. So that's going to be 15 and then 1 1 carry. And then the next one is going to be 5 and 8. 5 and 8 is equal to 13, and that one is 14. So 4, and again 1 1 carry. And finally we have this 3 and this 1 4 and 1 1 carry 5. So it's 5 and this point. 5.450 meter square. Okay, the unit is meter square. This is the area of the sheet. So now let's scroll up and come to the question. Yes. Now what they are asking is, the first part is what we have solved, which is the area of the sheet required for making the box. Okay, so I'm just going to make a note here. That is equal to, what was the exact number? 5.45 meter square. So 5.45 meter square. So thus the first problem is done. Now what is the second problem? They're saying the cost of the sheet is this, rupees 20 per meter square. So very simple and straightforward. If 20 rupees is the cost for 1 meter square, then what is the cost for this much meter square? All you have to do is just multiply. So I'm just going to do it right here. That is equal to 5.45 into 20. That is equal to 0 as it is. And then 5 to the 10, 0, 1, 1 carry. 4 to the 8 and 9, and 5 to the 10 again as it is. And we have to give one decimal. So we'll give one decimal here. And this is going to be 1090 rupees. So that is the cost of the sheet. That will be the total cost of the plastic box in order to make it with these dimensions. So thus in this problem we have seen that how a cuboid was given to us. Okay, a cuboid was given to us, but with a special condition that it does not have a top. The top face of the cuboid does not exist. So it's not our normal cuboid where we can directly use the surface area formula. We have to draw the cuboid. This is very important. You have to visualize the cuboid, assign proper dimensions to it, and then try to solve it step by step, that what are the faces that exist in this cuboid, and calculate their area. So this is the problem number 1.